Hello. Common rail engines. Are you looking for information on common rail engines, such as common rail fuel system, injection module, fuel timing control, fuel quantity control, and how fuel efficiency is improved through these common rail systems, and how Tier 2 and Tier 3 NOx control is achieved? You're in the right place. Let's go ahead and watch the common rail system in detail. Welcome. You are watching Diesel Chip videos presented by Ram Govindasamy, one of the chief engineers of Diesel Ship. To make it nice and easy to understand this complicated system, I've split this video into four main chapters. Chapter 1 covers the common rail components, where I will be showing you the line diagram of the common rail system and explain you various components and their functions. Chapter number 2 is a simulation of fuel circuit when the engine is in stopped condition, that is standby condition, where the fuel just circulates throughout the engine without any function. And the third chapter is the main simulation of all units firing. Here I will be showing you how the fuel enters the engine and how it is pumped through the lobe pumps and then the common rail function from there, the valve groups and to the injector. As number three chapter covers the fuel timing, chapter 4 will cover the fuel quantity control, right? Timing and precise metering and control is the main function of a fuel injection system, as you know. So this video is split into four main chapters. If you are someone who have already worked on a common rail engine, you can feel free to skip chapter 1. But if you're new to common rail system, I recommend that you watch all the chapters to understand this better. Let's get into the topic. To action. This is part 1, chapter 1. You must watch this in full to understand various components of the system, to understand its operation as well. If you have fair knowledge on these components, feel free to scroll to the next slide. But if you have not worked and you would like to learn the common rail system from basic, please do watch because these are not the same as conventional engines. So this is pretty fairly new components. Okay. The brown line or the yellow line that you see here, this is the fuel inlet line. This fuel comes from the fuel booster pump from the fuel skid. It comes at 12 to 15 bar depending on the engine size and the configuration, all this stuff, right? And the green line you see here, that is the line goes back from the engine to the fuel system, right? It basically goes back to a buffer tank or a mixing column, whatever we call it in your ship. That's how it goes back to, right? So the first component that I'm going to introduce you to is the fuel pump cam. This is a three lobe pump. Okay, the cam does the pumping action, right? This is a lobe type cam. And as you know, these are constant speed engines, so the pumping action remains the same throughout. I'll explain you when I go to the next component, right? And the next is the fuel pump. You see two fuel pumps. Obviously, we cannot have one fuel pump. We should have redundancy. But then there are calculation depending on the number of units, amount of fuel required, pressure required, number of pumps may vary, but the minimum is two per bank, per side, or per engine if it is not a V engine. Right. The next component that we're going to see is suction throttle valve throttle magnet. Let's say when the engine load goes up, it will consume more fuel, so the pressure will drop in the common rate, right? So the pumps has to pump more fuel. What happens to this pump? This pump does the same kind of displacement. There's nothing changes. What can change is the fuel flow. So the throttle magnet does the function of controlling the flow through the pump, right? If the load goes up, the pressure will drop, so it will open more, allow more fuel to be pumped, so more pressure in the common rail, so the load can, the increased load can be handled. At the same time, if the load goes down, engine slows down, consumes less fuel, so the pressure in the common rail will go up, so the throttle magnet will close down a little bit, throttle down, so the pressure is maintained at certain bar, certain pressure required for a particular load, right? The next component that we're going to see is accumulator or common rail, right? So you have a cam, you have a pump, and the throttle magnets are controlling the flow. Then you should have a container to contain this fuel, right? That is called an accumulator. Why is it called a common rail? Because these are connected to one another, right? I'll show you here. You can see these are connected, right? These are connected. So pressure across these accumulators are the same, even though they are connected to different pumps. Okay, but then they are still interconnected. So this is called one common rail. That's why it's called a common rail engine, right? The next component that you should see is a valve group. Okay, and in my previous introduction, I told you that these engines are the engines that is going to comply with your tier 2 and tier 3 emission related regulations, right? Why? Because a mechanical engine, please listen to what I'm going to tell you, how and why should we go to this common rail engine, which is so complicated and it does require, the help of electrical engineers. Days are gone that only the ships require more of mechanical engineers and less of electrical engineers. Things are changing slowly. The engines these days need as much mechanical and electrical engineers as well, right? Why do we need electronic engines? Electronic injection is so flexible, right? To handle the emissions, to handle the emission requirements, the engine should have certain quality of injection, flexibility of injection. There has to be flexibility in injection. Say if you want to alter an injection, right? We have VIT, we have FQS, all these things in a mechanical injection system. But mechanical injection to aid anything has to have a mechanical action. Mechanical action comes through linkages, comes through due to that there is a lot of wear and tear, and there is going to be a lag. There is going to be a lot of other associated issues with mechanical actions, right? But whereas a electronic injection is so flexible, so the complete injection, the heart of injection depends on this valve group. This valve group is 5 or 6 port valve. So the main functions, I'm going to list the main functions. Please listen to me carefully. When the engine is stopped, it is going to circulate the fuel, right? The fuel has to circulate through the valve group to maintain, to prevent solidification and to maintain the temperature at certain temperatures, a preheated condition, right? So like jacket cooling water, fuel also is circulated, which we all know. So this does the fuel recirculation. Then the fuel has to be always closed. So positively closed system. The high pressure from accumulator, from the common rail should not enter into the injector unless it is required to do so. That is when the injection commences, right? So that is another function. The another function is it has to remain closed. I told you. The another function is start the injection. When the control module says it commence the injection, it has to commence. And then when termination of injection, how does it terminate? The valve group just simply opens the drain port. So the fuel immediately drains, meaning the fuel from the injector all the way to the block is completely drained, right? So this also does function of that. And the final function is that anything happens to the injection component, say a big large leak, or anything happens and the emergency shutdown has to be activated. The first thing gets command in this electronic injection is this valve group. This valve group immediately shuts to the position that you see here. Right now, what you see, it's a completely shut position. So this has to happen. And then the final thing is that this valve is an active valve. It is monitored by the injection control module, and this is giving regular feedback of its condition. If the feedback is not received, or if the feedback is different from it is supposed to be, the engine throws an error and it does not start. Even one failure of one valve group will trigger an alarm and the engine will shut down, or if it is in stopped condition, it will not start. Right. And then the fuel injector is a mere fuel injector. If the pressure is above certain bar, it will open, inject, atomize the fuel, and then when the pressure goes down, it will close due to the spring force, right? And then flushing valve. Flushing valve is one of the main valve that aids fuel circulation. When the engine is running, this valve is closed, right? When the engine is stopped, this valve is open. So what happens is it aids the fuel circulation. The yellow line or the brown line to the green line is connected through a flushing valve. So flushing valve is very important, right? The next one is safety valve. Okay, any pressure vessel has to have a safety valve. Accumulators, common rails have certain pressure. It varies from 1,200, 1,200 to 1,900. 1,950 is the safety valve opening setup for this particular engine. So this has certain pressure to maintain. If it goes beyond, safety valve will come into action. The another valve is Rickmeyer valve. It is like it maintains the pressure through the engine, fuel pressure through the engine, right? It connects the inlet and outlet. We call it in Sulzer, we call it valve block or pressure block or pressure regulating valve. Whatever you call it, it is a simple spring-loaded valve set to maintain certain pressure in the engine, right? If the pressure is too low in a traditional engine, the engine the fuel pumps go on starving mode where there's a lot of consequential issues happen. So in a conventional engine, we had that kind of pressure block or a back pressure valve or a pressure maintaining block, whatever you call it. Basically, it connects inlet to outlet to maintain. Say if the pressure, incoming pressure is too high, it opens up so the pressure, required pressure is maintained through the engine. If it is too low, it closes to increase. So that's how it operates. It is purely a mechanical valve, right? I've tried to rush up through this particular slide, so I will be able to show you all the components. It is very important, as I said, if you are someone who have not worked on this kind of engines, this slide is very, very important. Let's move into the next slide. Thank you. Well, here I'm going to simulate the engine at stopped condition, where the fuel is just going to circulate through the fuel injection components, right? Okay, main thing that we need here is the fuel inlet and then the fuel outlet. One of the important element that I missed to explain you in the previous chapter is a non-return valve. This non-return valve here connects the supply, fuel supply, that is the yellow line, to the accumulators, right? When the engine is in stopped condition, this should allow the fuel to pass through this direction, right? At the same time, when the engine is started and the accumulators are pressurized, it will work in the opposite direction by pushing the ball down, and this acts as a non-return valve. It comes in effect only when the engine is stopped, right? Okay, let's move into the animation part. Flushing valve, this is the main valve that activates when the engine is stopped, which is activated by the control air, 7-bar control air, as you can see. The control air at 7 bar is pushing the flushing valve out, and you can see the fuel starts flowing in the direction it is supposed to be. If you remember, I did mention that the valve group has the function of circulating fuel through. So this portion aids in fuel circulation through the valve groups. As you can see, the fuel passes through the various components. Now let me simulate opening of the non-return valve for C. The ball has moved and the fuel is going through the accumulators as well. So the complete fuel injection components are now circulated by the fuel, right? The fuel returns back to the buffer tank as we already discussed. Right, we'll see the rest in the next chapter. That is going to be the main injection animation. We'll see you in the next chapter. Let's now simulate starting the engine, where the fuel will move through the pump to the accumulator, through the valve group, and to the injector. Injection, commencing of injection is very important. That timing is very, very important for a valve group. Same time, termination is also very, very important. When the fuel starts injection, basically it moves into open for few microseconds. And when it has to terminate, the fuel has to drain down. So you can see all that in this animation. Let's activate one of the valve group now. Right, the first valve group as activated. This is the best way I can show you opening and closing. I thought of different ways, but then this worked much better. As you see, the green line, these are the returns, right? This is what happens when the fuel terminates, the fuel injection terminates, right? So this is one of the very important factor. And in this video before, in the beginning, I forgot to show you the flushing valve is closed, right? As soon as the engine starts, the flushing valve closes. That is very important factor. And another thing you should notice is the fuel rail pressure. The fuel rail pressure increases with the load and decreases with the load as well. Okay, for certain load, the pressure has to increase. As the load goes up, the pressure on the common rail also goes up, right? So there is a calculation based on the mode selected. The engine can operate in different mode. This engine is particular MAN engine, and this engine has few different modes, which is emission mode, emission control mode, or fuel economy mode, or high power mode. These are the three modes that I have worked on. So at different modes, the characteristics of the whole injection module varies heavily, right? Right. I can show, I've already shown you injection, the timing. Yes, I've tried to, capture closest to the exact timing, but you might see some lag here and there, especially the springs. I've tried to simulate different ways, but this is the best I could try. But I hope, that doesn't really affect the functionality, but I'm sure you guys are able to follow the diagram and understand how the complete circuit works. Right. In the next slide, I'm going to explain you the fuel timing, right? So right now what you're seeing is the quantity, control of the fuel quantity, precise metering, and termination, injection. Everything is shown here. In the next slide, we'll see the timing. Um, Before we go into simulating the timing, one of the factor that I wanted to show you is how does the pressure variation is taken care by the fuel pump, right? I've already explained you when I explained you about the throttle magnet valve that it opens and closes by the control from the fuel pump module. Let's see it in simulation, right? Let me show you increase of pressure. Let's say the load has reduced on the engine and the fuel pressure has increased because the load has reduced on the engine from 1750 to 1800 bar, and then we see it has moved to 1850 bar as well. Immediately you could have seen that the throttle valve magnet has closed. It was three-quarter open, now it's only half open, right? And see, let's see, as soon as it opens half, it goes back to, the pressure goes back to 1750. I've tried to simulate the functionality of the throttle magnet. I hope this is very simple to understand. As I said, throttle magnet is the key factor in controlling the pressure in the accumulator, right? For any reason, if the throttle magnet does not work well, the pressure in the accumulator will either raise or drop, right? Drop is fine, we'll have issues, the engine will, kind of trip, but when the pressure rises, it is very dangerous. Still, there is safety valve which will take over and then reduce the pressure. Okay, let's move on to the next slide to simulate a pressure rise, okay, beyond safe limits and see what happens to this fuel circuit, right? Okay, let me simulate. Okay, as you can see, the pressure gauge is going to show you increase of pressure. For this particular engine, the maximum pressure, the maximum safe pressure is 1950. If the pressure touches 1950 or more, let's see what happens, right? The safety valve. Okay, I've shown in the yellow box here, you can see, the safety valve comes into act. The spring gets pushed and the safety valve is open. It's a mechanical valve, and the pressure on the accumulator is bypassed through the safety valve back to return line. So obviously the pressure in the accumulators will drop down. Very interesting factor here is that the safety valve has not closed. You can see the safety valve is still open. Okay, this is a philosophy by MAN because when the pressure rises beyond safe limits, that means that something has failed. And it is like a high pressure trip on a refrigeration cycle, right? As in a refrigeration circuit, low pressure is fine, but then high pressure is dangerous. Similarly, here it has to have a manual reset. How do we reset it? The only way is to stop the engine. So this way, MAN philosophy kind of they tend to think that when the engine has to be stopped, then the user realizes that there is something wrong and there has to be a fault finding involved. Otherwise, the safety valve will open, the pressure will reduce, safety valve will close, the engine will continue to run, the error will continue to occur. So for this reason, MAN has made it very strict policy here that the engine has to be stopped even if the pressure rises at one instance. Right. Let's move into the next slide. Last slide. In this slide, I'm going to explain you how the fuel timing is varied, right? When the load is increased on any engine, the fuel has to be administered more, and that way the power product produced is more, and that's how the power, the power change is taken care by the engine by producing more power or by reducing the power when the load is removed. So I'm going to simulate increase of power. I would ask you to watch here, and then you see as soon as this goes up, you'll see that the throttle magnet is going to open more. Yeah, obviously the pressure gauge will raise, and then here I'm going to show you the valve opening time, right? See, what happens in a conventional engine is that we have a helical groove and a plunger turning and all this stuff, right? Mechanically, we are increasing the volume of the fuel admitted into the um, injection components. But here, it is really good. You know why the electronic engines are so successful is because the timing, metering, injection, everything is so precise, so you know flexible without relying on any mechanical action, right? If there has to be a mechanical action, there has to be so many mechanical linkages involved, lagging. So there's a lot of other factors that it is not so easy. This part, what you're going to see on the screen, this is what really makes an electronic engine very successful. So, is it really a common fail? Probably it was during the early days, but then it is really not any more common fail. It is definitely a common rail, and it is a very successful technology these days. Without common rail, I don't think so. We will even be able to move into tier two, right? Tier three with conventional injection, I'm sure it is pretty much not possible at this stage. Not sure what's going to happen in the future, but it is not possible. Right, let's come back to our video. Let's simulate a load increase. So please look at load on the engine and then look at the throttle magnet as well. Load has moved, and now the throttle magnet has to move up. Okay, the throttle magnet is moving. It's opening because now the load has increased, due to which the load is increasing, right? It's about 1750 bar. Right now, the pressure is increased, right? What actually affects the load to increase is the timing, right? The opening timing of the valve group should increase. Oh, okay, so now from 0.30 microseconds to 0.40 microseconds, it has increased. It's very hard to capture because I have tried to set it up in my animation, but it's really hard to capture that microsecond increase. See that slowly it just stops for a second. So you can see I've shown double arrow, and then probably I would have shown triple arrow as well. You can see the valve group, it stops for a microsecond more than it was actually doing on a normal load, like before the load has actually increased. So what happens if the load reduces? The things happens in vice versa, right? The throttle magnet is going to close, the pressure is going to be controlled, and then the valve opening time is going to go back to wherever it was, right? Hence the fuel injection module and the rest of the things about common rail system. As it is, if you take a manual of MAN or even Wärtsilä Sulzer engines, it's very hard to understand. Even I found it very, very difficult to follow and understand this system. It took a while, and then I had to do a lot of research to bring you this simplified version. We might have missed something, but then see, this is the best we could do to bring you in a simulated format. And we really hope that we did do some kind of justice for to make you understand and to introduce you to common rail systems. Thank you for watching. This is Ram Govindaswamy, one of the chief engineers from dieselship.com. Thank you so much.